All right. Thank you very much for the invitation. It's a pleasure to be speaking in my home, but to you all. So yeah, at least I apologize. It's going to be very much a symplectic focus, but at least the mutations aspect, I'm sure at least Alex Capri can relate to it a lot. So yeah, it's first. This is joint work with Roger Casals from UC Davis. Here he is, and so the idea, it got very famous, these kind of embedding problems on symplectic geometry after Gromov's non-squeezing theorem. So you start with ellipsoid embedded in R4, and then you have your fixed symplectic manifold for manifold, and then you ask yourself when can I embed this ellipsoid? And Gromov's non-squeezing theorem was proven for the ellipsoid 1,1, which is the standard ball, that if I want to embed it in disk times R2, so I have complete infinite volume on this direction. But here I have some the restriction of the radius. My radius needs to be at least 1, despite the fact that I definitely have, no matter how small the radius is, I have a volume preserving embedding. But the symplectic embedding, the radius needs to be at least 1. So this start the whole series was an open question if like volume preserving maps were kind of like the same as symplectic symplectic embeddings. And so this result proved not. And well, it's an easy consequence that I can upgrade this to E1B. So there is so this kind of like results of symplectic embeddings usually has 2 aspects. One of them is the constructive aspect for embeddings or for packings of different ellipsoids. And here's a non-exhaustive list of people that have been working with these embeddings, most of them with ellipsoid embeddings, but some with like Gunther working polydiscs, and Ramos and Seppi, they worked on Lagrangian products and things as such. So there is the constructive aspect, and there is an obstructive aspect. There is also, which is usually done from some sort of symplectic capacities that first started with Gromov, with this work of Gromov and various other people. Perhaps I should put here also Viterbo, and more recently in dimension 4, there is Michael Hutchins' ESH capacities that allow us to do the obstructive aspect. So this talk is going to be essentially on some constructive aspect of this theory, and mostly recovering some known results, but also giving some other results. So if we use both the constructive aspect and the obstructive aspect, so McDuff and Schlenk were the first to study this case in a big generality for embeddings of ellipsoids inside the ball, and they discovered that there is this sort of like staircase behavior. So I can define this function here, Cx of A, which is how much can I scale down, we would think, or what's the infimum of lambda such that I need to rescale my simplex form to be able to embed this ellipsoid. So it's if you think about one of CA, it's like it's asking how big of an ellipsoid can I get inside my fixed X. So this it's usually I always think about the inverse of this function when I'm thinking about this problem. But so they showed this very exotic behavior of this function. So there is one obvious obstruction, which is the volume obstruction. The volume of the x lambda needs to be bigger than the volume of the ellipsoid. So there is this curve here of the volume obstruction that so volume goes like the square, so the inverse goes like the square root. So it's a function that goes like some square root of a. And surprisingly enough, this function has this sort of like staircase behavior, where you start to be able to linearly increase the volume of the ellipsoid. Then you get a point where you start you start increasing the value of a. So somehow you start increasing the ellipsoid, but you keep the same. You can embed in. You keep kind of like reducing keep the same lambda, right? But in a way, the volume of the ellipsoid is expanding as I increase a. That's why I say I always think in the reverse setting. So you keep the same volume of your symplectic manifold, but you start increasing the volume and shifting the shape of your ellipsoid until you are able to hit the volume obstruction. And then this game goes on and on. And then there is some sort of accumulation point. And all these points where you hit the volume obstruction, the value of A is associated to these odd Fibonacci numbers. And then the accumulation point is related with the golden ratio. So this tau is the golden ratio plus 1. So they have this very exotic behavior. And then there is another part of the stair which has some sort of like finite stairs. And then after some point, it just coincides with the volume obstruction. So there is this very bizarre behavior that after McDuff and Schlenk proved it for the ball, it was also proven by Fenkel-Müller and then Cristofaro-Gardiner for the polydisc and inside the ellipsoid E23. The aim of our talk is to get to show which spaces allow these infinite volume, infinite sharp embeddings, where the volume obstruction is the only obstruction that there is. Okay, so what was Casals, Roger Casals' idea is, oops, sorry, I had something, okay, let me go. So there was like this paper of mine where I construct infinitely remaining monotone Lagrangian tori in CP2 that was very much inspired by the work of Galkin-Musnich. And so it's related to this idea of almost-toric fibrations that encode in the symplectic geometry side these sort of mutations that first appear in this draft by Galkin-Musnich. So before this, actually, I think in 13, but I was just not very much aware, the combinatorial aspects of this polytope mutation was already worked out by Mohammed Akhtar and Alex Kapsik. And now that there is also some work of Kapsik and other collaborations, other collaborators. Somehow, I think I forget their names, and then I had it in a window here, but I just closed it. So perhaps I can find it here. So it is Capsic where HK. Oh gosh. I'm just not finding it. Oh yes, New and Prince. So they also work out this mutation for the Opezzo surface before I did my work on the Opezzo surface. But anyway, and also there is a famous work of them with Coates and also Sergei Galkin. So, but we have this interpretation of these mutations in symplectic geometry that's given by these almost-toric fibrations, where we have these, we introduce these nodes that correspond to some singular fiber of my Lagrangian torus fibration, and we use it to mutate. But what you can note is that what Roger noted is something very simple that I just was not paying attention on. That is that if we keep if we just mutate with respect to these two nodes and keep this one fixed, I always have a corner of an ellipsoid. And then because I'm able to make this kind of cut as close to the vertex as we want, in a limit, I would get a full volume ellipsoid embedding inside CP2. And these polytope mutations are associated with this Markov triple, which is the solution of this sort of equation. So mutating just two of the corners corresponds to me to fix one of these variables to be 1, and then the other two variables mutate like this. And this arithmetic mutation corresponds to the polytope mutation. And then one just note, because we have this kind of like a full volume embedding, it is not too surprised to note that the solutions for these equations are precisely pairs of odd Fibonacci numbers. So you just start you just start with 1, 1 if you want, but then the first mutation gives you 1, 1, 2, and then you just, this is a base of induction, and you just see that the odd Fibonacci numbers mutate accordingly. So the solutions of these Markov equations, pair of odd Fibonacci numbers, but these were related to embeddings inside the ball, right? And the thing that Roger was missing was he was not very attentive. He just didn't have a way to show that, well, I need to delete a line to be able to get the ball, right? So you need to show that inside this region here, that I'm allowed to make as small as you want, I'm able to find the line. And that's going to come later in our talk. So soon I'm going to go into more details about these almost-toric fibrations, but I want to now to already state the theorem that was proved by us, but it also appeared on a paper that came on the same time, so we independently found this result, that there is was not so, I mean, they do use this Roger Casals idea, but their proof, well, I guess for this specific theorem is mostly their proof is different. Yes, their proof is different than ours. So it's just that they do a little bit more than just this, well, considerably more than just this theorem that I'm going to state, which is the following. You consider these these polytopes, which are reflexive polytopes, and you need to delete some divisors out of the boundary, but in some situations you also need to delete a divisor and some Lagrangian spheres that I will explain promptly. But the result is, if you look at these polytopes that you're seeing there, forget these decorations and forget the blue line. You're going to see what we call a toric domain, which is just an open symplectic manifold described by these polytopes like this. For instance, just disregard this inner decoration and disregard what is the blue wedges. So all these symplectic toric domains, they do admit infinitely many sharp ellipsoid embeddings. So there is infinitely many ellipsoids that embed with full volume inside these spaces. And well, if you will, since I'm here in the setting of algebraic geometry, you can just consider this decoration. Then you get a polytope. Then you're going to get an orbifold, a fun orbifold, and then you just delete the singular divisor. Is the same statement, of course. And so this is the statement of the theorem. So I'm going to come back to this picture. but I need to give you some geometric intuition about these almost-toric fibrations. So before that, I'm just gonna state what I thought. There is this paper that came at the same time, infinite staircase and reflexive polytopes, by these very photogenic people here. So I think if you zoom too much, the quality of the picture is not it's not too good. But so Alessia Mandini, then Cristofaro-Gardiner, Annalita Pires, and Tara Holm, and so they show the constructive aspect of the theory, but they also worked the obstructions to prove that these the 9 corresponding domains, which call toric domains, they also admit this sort of staircase behavior, and moreover they find another 3 that corresponds also to reflexive polytopes, blowing up once here or twice, and then one mutation of blowing up twice, CP2, that also admit a similar staircase behavior, but they don't hit the volume bound. And they have good reasons to conjecture that these are all the domains with these infinite staircase behaviors. Okay, so I'm on this page now. So, so our proof involves 2 points. First, the mutation aspect that use these almost-toric fibrations, and also almost-toric geometry was developed by Margaret Sampson, and also we developed the notion of symplectic tropical curves, very much inspired on the work of Mikhalkin. But our situation is much more flexible to ask something to be symplectic than to ask something to be holomorphic. Even if you're taking a limit of a j, it's just much easier to ask something to be symplectic. So almost-toric fibrations. So I was saying that these mutate to some in a two-step mutation out of this, you can get to this triangular shape polytope here. And then the mutations of this polytope, like bringing all these nodes passing through and bringing this pass through, this is how you're going to see the ellipsoid embeddings corresponding to these guys here. But very much reasonable question to ask is why I do not have the result for E for 5, right? I get infinitely many ellipsoid embeddings full volume inside this blow up, but why can't I get for E for 5? And it has to do with the fact that the T singularity corresponding to this guy here, if you kind of just disregard this node and you think of this as an ortho, is not of AN type. So when you smooth it out, in this example, you're also going to have an RP2. And so this kind of like obstructs me to be able to have a smooth representative of what would correspond to this divisor here, even if I use the spheres. So for this space here, this is the E23. I do get my result because I'm able to delete this symplectic divisor here, plus the Lagrangian spheres that were living here on the top. And on this complement, I'm able, what I want to say, I'm always able to find this configuration, this sort of configuration inside my mutated things. But because here I do not have a divisor, here I can push a node to the point and can get a point here, but here it does not collapse. This is what obstructs me. This is why we don't have these infinite volume embeddings in E45. And it's also why, because it's also a reason that I can claim that I can get, say, E14 inside the ball, but it's not true that you can get the ball inside E14, even though they are both related by mutation. It has to do with the fact that I can find a line in this small neighborhood, but there is nothing that's smoothly representing this edge here as a closed cycle. Okay, so in these last 10 minutes, I want to finishing with some of these ideas of symplectic tropical curves. So, our idea, as we said, for example, in CP2, we have this. We can clearly see this. This is an ellipsoid, and you can clearly see it embedded in CP2. But if you want to embed inside the ball, you need to delete a line, at least a symplectic line. It doesn't need to be holomorphic. Algebraic geometry. You need to delete some line that you can prove that is that's isotopic to this one. So all lines in CP2 are isotopic, pretty much. So the point is, in all these fibrations, I can draw this sort of symplectic curve that it kind of here it kind of looks like tropical the way I draw it, but there are two things that I want to mention. This slope is not necessarily encoding the direction of if you just look at this picture, it doesn't really look to satisfy a balancing condition if you're really thinking about tropical geometry. But what we are doing is much more flexible. We can even go in a curving direction. Why? Because what needs to satisfy the balancing condition is the cycle that I'm transporting around the legs. But once I choose a cycle, for instance, the cycle corresponding to the vanishing cycle, it's not quite a vanishing cycle, but the collapsing cycle for this node here. To get a symplectic surface, I only have one direction that I'm forbidden to move. There is one direction where I move it, that whatever I move becomes Lagrangian. In all other possible directions, whatever I move becomes symplectic. So I just need to, I can get some curvy things like this. And the only thing that I need to care to satisfy some balancing condition is on the homology of the cycles. Is not on, let's say, the amoeba picture of it. It can be very curvy even. Okay. So we are much more flexible than on the holomorphic situation. But what we want is to find this this sort of symplectic line, and you can show that combinatorially you can always find this by putting some multiplicity on the legs here that are essentially related with the Markov numbers. Look that these are the square roots of the numbers that appear here. And of course, it goes with always 3 here in the bottom because it's representing the class of the line and needs to intersect the anti-canonical divisor 3 times. So you can always kind of like draw this picture, but I want to also mention another nuance here is that, well, what happens when you come with multiplicity towards a node? Because if you are very naive, I mean, coming with multiplicity here is not bad, because over here I have a circle, and then I can come with 3 parallel guys that are just collapsing here. I don't create any sort of genus, let's say, and then I can just glue around. I don't create any sort of genus. But if I'm naive on how I arrive to my singular node here, let me draw like this. So this glues to a Lagrangian torus. Oh, what I'm doing. So let's just draw the neighborhood of the singular node. So if I'm very naive and I'm coming with parallel cycles like this, these guys, they do have some transverse intersection here. So I cannot just kind of like smooth them out without creating genus. You see? So the situation, there is, I'm just saying there is some technical complications here that the situation, the projection, when I get very close to this node is not actually over a line, but it's a projection like this. And not only that, if you think about this thickened torus here, the boundary of the disks that I take, they are kind of like linked. They are all self-linked ones inside this thickened torus here. So there is some very technical complications to working with this. But the theorem is that it always we can find all of these sort of like the configurations of divisors here, inside each one, so for instance, here we have 3 divisors here, we can get configuration of 3 divisors here in this very small region here, and without the Lagrangian spheres. So this allows us to show, for instance, that E45, and because this region can get infinitesimally small, you can ensure that E45 actually embeds with full volume inside this toric region, given like this. Because I'm able to identify this configuration, and I push the nodes here to become Lagrangian spheres. So I'm able to identify these configurations of symplectic curves and Lagrangian spheres inside this small region here using these symplectic tropical curves. And that's how we show that these infinitely many ellipsoids that we can get out of mutations that a priori we only know that's embedded inside this closed space, we can get them embedded on the corresponding regions, because we can delete the divisors. And but I do want to emphasize something. Working with only one divisor, the picture just looks kind of nice like this. But once you have more than one divisor, if you try to draw things naively like that, you're going to be causing a bunch, because symplectic curves, they can have negative intersections. You're just going to be causing a bunch of positive and negative intersections. Of course, the total intersection will be 1 because you're getting the right homology class, but you're going to be creating a bunch of positive and negative intersections. And then you cannot apply any result to say that this is actually, this is definitely not going to be isotopic to the configuration that we started with, where the number of intersections were precisely number of the topological intersection. So in this very simple case of trying to find these 2 classes of H1 and H2 inside this first mutation here is easy. You can just get it like this. But as you mutate around and you try to get these 2 representatives here with the one intersection, they intersect once on the nodes, I mean, not just topologically. You do need to do some construct some very complicated picture here, where these kind of numbers here, they encode cycles being linked, the boundary of cycles being linked like this. And then you do need to really make a mess on this very simplest. When you're considering more than one divisor, things already get quite complicated if you want to get the result. So further directions is that, well, we can, instead of considering, so 2 minutes, okay. So instead of considering just ellipsoid embeddings that are embeddings kind of like of polytopes like this, with this vertex here, I can consider, as I told you, I can move these to become, oops. No. What's going on? Okay. I can choose so that I can move this to delete this node and bring a Lagrangian sphere here. And then polytopes like this, they look like some normal bundles of these Lagrangian spheres. And then if instead of myself mutating this vertex and this vertex, if I start mutating with respect to these 2 vertex here, I'm gonna get infinitely many types of neighborhoods of T star of S2 embedded in P1 times P1. And also I can play with deleting this divisor as well and get embeddings of different shapes of neighborhoods of T star of S2, one embedded inside another with full volume embeddings, and can work to different sort of neighborhoods as well. And there is also, as I mentioned, combinatorially, higher dimensions mutations were already worked out, but it was not completely worked out. The almost-toric aspect of it, or what would be almost-toric mutations. So, for instance, in CP3, for me, it's already not obvious at all. I can make a sense of mutating this vertex, but I cannot, and I can make a sense of mutating edges as well, but I cannot make a sense of mutating this vertex and then mutating this other vertex afterwards, because things start, the singularities, they start interacting in a very complicated way. So, but still, it's one direction to think harder on how things worked out in higher dimensions. And I want to finish here now.